Augmented reality is becoming widely available thanks to the widespread use of mobile devices such as smartphones and tablets. Popular categories include lifestyle apps such as furniture placement, utility apps such as measuring tapes, and educational apps such as celestial body visualizers. There are other types of AR besides mobile, and researchers are currently exploring new devices and new interaction techniques. But rather than creating novel techniques, this work focuses on how to create interactive prototypes within the existing mobile design space. Currently, creating fully interactive prototypes require coding and extensive programming skill. So we wonder, how can designers prototype interactive AR without the need of coding? Well, for other interactive mediums, such as websites or screen-based mobile apps, designers have a set of rapid prototyping technique at their disposal. They use sketching to quickly illustrate ideas, for example, on a whiteboard depicting different screens of a mobile application. Sometimes they use paper prototyping, maybe to get a representation closer to the final size. To support interactivity without programming, they can use the Wizard of Oz technique, where one designer can play the role of the computer. And finally, all this work can be recorded to illustrate a scenario or to explore multiple ideas with a technique called video prototyping. One drawback of these rapid techniques is that the output is a non-interactive video. The designer can only press play and watch it. To create interactivity, these representations are used as guidelines for programmers to translate them into symbolic representations, generally using programming code. Here, we want to support a workflow that allows designer representations to be reused. So instead of being disposable guidelines, they will be essential parts of the interactive prototype. Okay, so how can we do this for AR? First, AR programming has a heavy use of realistic 3D models, but we should also be able to work with simple 2D sketches. Also, to animate these objects, designers need to define curves, timings, or even detailed keyframe animations. However, designer can simply enact the animation with a gesture, in a similar way to the Wizard of Oz technique. In contrast to traditional video prototyping, where the scenario is recorded at the end, for AR, we need to record the scenario at the beginning to capture the spatial properties of the environment. With all this in mind, let's introduce Rapido, a tool that allows the creation of interactive AR prototypes using demonstrated examples. Let's try to prototype an AR furniture app. It looks simple, but has many details that could be easily ignored while prototyping only with 2D techniques. Rapido supports 3 phases: video prototyping, programming with examples, and testing. We start by capturing a video background. In the scenario, we want to be able to place a lamp in different positions, so we make sure to capture all those angles in advance. We can draw sketches to represent a catalog, a circular marker, or a lamp. The user should be able to select an item from the catalog. In Rapido, we can demonstrate user inputs by pressing the Record Input button. In this case, we perform a tap gesture on top of the catalog. By default, sketches are attached to the screen to represent menus or items, but they should also be able to be pinned in the 3D world. To pin the lamp to the user focus, we create a link between the pin action and a yellow focus square. The focus square position is calculated as the intersection between the closest plane and a ray casted orthogonally from the center of the screen. Next, the video shows the user moving the lamp to the table. To signify that the lamp's position is being edited, we want a floating animation. With Rapido, we can create animations by pressing the Record Animation button and drawing an animation path with a finger. The user should now be able to move the lamp from the floor to the table by panning with a finger on the screen. After performing the user's pan gesture, we see a red target appearing on the scene representing the corresponding word tag. The position of the world touch is calculated in a similar way to the position of the focus square. The only difference is that the starting point is the location of the finger on the screen. We will now move from the AR interface to the overview interface. In this phase, we turn the video prototype into an interactive prototype. We can see that every action that we created on the tablet is shown in a timeline view, like in a video editing application. The timeline contains tracks for the demonstrated user inputs and the corresponding actions. Designer representations generally work with visual states like a user flow depicted by screens of a mobile application. This linear representation uses a concrete scenario. However, a computational state machine should be general and cover not only this scenario, but any other sequence of user inputs. Rapido infers an initial state machine from the linear states identified in the timeline. At the top, we can see that Rapido assumes that every input generates a new state with 6 placeholders. Every action that is below a placeholder will be added to the corresponding state in the diagram. By default, Rapido enumerates the states, but we can type in more descriptive names. For example, selecting an item from the catalog, placing the lamp, observing the selected result, and finally, repositioning the lamp. We can now test the interactive state machine on the tablet by pressing the test button. During testing, the state machine diagram will highlight the current state and the current transition to help debug the prototype. In less than 10 minutes, Rapido enabled us to create a video prototype of a furniture placement application and turn it into a fully interactive AR prototype. For more details on Rapido, read our paper. You will find an analysis of the related work and a discussion about its current limitations. We just cover a small portion of what Rapido can do and its opportunities to support many other types of AR devices. To which extent this approach could work for designers in the current practices will require further studies. But we hope to inspire other researchers to combine designer-friendly representations with symbolic representations for the creation of interactive AR prototypes. Thank you.